Next, we're going to explore some metrics that we can use both quantitatively and visually to understand the performance of our models. So the key knob that we have to play with in here is the threshold. In addition, once we have built the model that and we've explored which features are relevant, then really the only thing that's left to go from the computational predictions, the quantitative predictions of the model, which are probabilities, into decisions, into classification, is the threshold. And as we're going to explore, this affects our choice of threshold affects a number of different metrics, which we're going to see now. So the first one that we're going to focus on is accuracy. As we've seen already when we described the confusion matrix, the accuracy is the ratio between the total number of accurate predictions that we have, so true positives plus true negatives, divided by the total number of samples in our data set. So let's think for a minute about what happens as we move our threshold around. And I think the easiest way to get some intuition into what's going on here is to go back to the standard curve of our logistic function, where the threshold is our horizontal cutoff line, right? In this case, it's set at 0.5. So what we want to ask is, what happens as I move this line up or down? So if we move the line up, if we make the threshold higher, what we're saying is we classify less and less things as only the things that are above the line are going to be classified as belonging to class 1. Now, you can think in the limiting case, what happens if you move the threshold very, very close to 1? Only a few things that are up here that have extremely high probability will be classified as belonging to class 1, and everything below it, the bulk of your data, will be classified as going down to class 0, and vice versa if you move the threshold down to the bottom. So if you think about what's happening in this curve, then this plot over here should make a little bit more sense. What happens is we're looking at if we move the threshold higher, as I was saying up here, because we are basically sending the entire data set below the line into class 0, inevitably we will have many false negatives, because we're saying basically almost all the data is going to be classified as being negative, as being in class 0. But chances are not all the data belong there, which means a lot of those classifications will be false negatives. And conversely, if we move the threshold very low, then we're leaving most of the classifications as going to class 1 up towards the top, but that's probably not true. There's going to be many data points in here that should have been classified as in class 0, and therefore we will have many false positives. So we expect the accuracy to be maximized somewhere in the middle. Now, it doesn't have to be exactly at 0.5, and that'll depend on the structure of the model, but overall we expect that our accuracy as a function of the threshold will be something that will go sort of up somewhere in the middle, but as we make the threshold either very large or very small, it should go down. We expect our accuracy to go down for this reason. So in general, the accuracy does go up as we the precision now, as we switch to precision, does go up as we increase the threshold. And the reason is because as we increase the threshold, remember, we go back here, we do have more and more false negatives. As we move this line up, we have too many points below the line that don't belong there, so we have more false negatives, but we do have fewer false positives. And since precision is defined as the ratio between true positives and the predicted all of the data points that we predict as true, then as we increase the threshold, we will have fewer and fewer of these false positives, and so in general precision will tend to increase. But it is important to keep in mind that it's possible for precision to go down a little bit as we move the threshold up, and you should convince yourself of why. You should think of the fact that these are not, as you move the threshold, which means as you wiggle your model, both of these are quantities driven by your predictions. They're not static fixed properties of the data, which means as you increase the threshold, this denominator can also change. And so you should do a little bit of an exercise on pencil and paper. Imagine what happens if you have a mix of true positives and false positives, and what happens as you move that threshold up. It's a very instructive exercise to realize that because this denominator also depends on the model itself and is not fixed in the data, even though your true positive, your false positive number tends to go down as you increase the threshold, it's still possible to get precision to decrease a little bit. Recall, on the other hand, has a different behavior, because recall is defined as the ratio between the things that we classify correctly as positives over all the things that are fundamentally positive in the data set, the true positives in the data. And so if we go again back to our diagram here, as we increase our threshold, then we have more and more false negatives. So as we take our threshold up, as we discussed, we have more and more false negatives, but the denominator doesn't change. This denominator is just whatever's in the data. Nothing we do to the model changes the denominator of the recall, which means that the recall curve does go uniformly and monotonically down. So if we look at these two curves together at the same time, they have this kind of structure, and so there's sort of a trade-off. This has echoes of the bias variance trade-off we saw earlier. These two quantities are in a little bit of tension with one another, and there's in general some kind of optimal point roughly around the center, but it doesn't have to be exactly at 0.5. The specific location will depend on the model, where the tension between these two is sort of optimally balanced out. And so one useful way to think about these quantities is, rather than plotting both of them separately as a function of the threshold, is to plot them together as a function of one another. And what we're doing here is a single plot that actually summarizes all of this data into one single line for different thresholds. So effectively what we're asking is, as I vary the threshold, what precision do I get and what recall do I get? And for every value of the threshold, I get a specific value of recall and precision, and I plot a point, and now I plot all of those points. So this is, in a sense, a history of the entire model being explored as a function of threshold. And so before we move on, what I want you to do is stop the video and think through, where in this curve should both low and high thresholds live, and why? So to convince yourself that your intuition tells you why is a given part of the curve corresponds to low thresholds and another one to high. At very high thresholds, the precision goes up, as we've seen, because effectively at very high thresholds we have no false positives, right? Remember the curve. So there's no room left really for false positives. On the other hand, recall is terrible, because as we saw at high thresholds, we also have precisely that bottom of the curve gives us tons of false negatives. So the denominator of the recall definition goes up, gets very large, and so we end up that at high thresholds we're in a situation where we have good precision, high precision, but very poor recall. So we're going to be out here, basically. And so the curve begins looking like this. Now, as we begin lowering the threshold, as we go to lower thresholds, we start losing some precision, but we start gaining recall, precisely because that false negative rate begins to go down. So it's useful to think about what would be sort of the dream predictor, the perfect predictor. What would be a classifier that works perfectly, and what would this curve look like? And so this curve would look like, in a perfect predictor that makes absolutely no mistakes, that no matter what, never has any false positives and never has any false negatives, then precision would always be 1. Right? The precision would always be 1, and recall would effectively also be 1. So in a sense, the curve could only exist on those two values, which means that our real models are always, obviously this is not a normal function plot, so we'll never achieve that, but real models are aspiring to look like this L-shaped orange line in here. And so the reason why this idealization is useful is because it helps us then think about, what is a good way to interpret this curve? What do we want this curve that we have to look like? Well, we want it to look like more like that L. And so one useful metric then is to quantify what is the difference between this curve and that L. And a simple quantitative way of measuring that is to ask, what is the area under this curve? The more it stretches and stretches to become like an L, the more square it gets, well, the more area it gets. The area of this region bounded by the orange curve is 1. This is really a square. It happens to be drawn on a picture that is rectangular in shape, but it's the vertical scale goes up to 1, the horizontal scale goes up to 1, from 0 to 1, 0 to 1. It's a square of area 1, which means that if we measure the area under this curve, the closer this area gets to 1, the better our model will be in terms of its precision recall structure. So this is one quantity that we can look at, is the area under this particular curve. Now we're going to see actually that a common curve is to look at comes next. It's called the ROC curve. But in general, this idea of comparing the real shape of our curves to that one of idealized ones and looking at the areas between them is a good way of effectively having a single number that captures the complexity of the situation, and that's why we ask what these areas are. Now there are other metrics that we can compute from these same numbers. So, for example, the false positive rate is the ratio of false positives to false positives plus true negatives. So in this case, it's the same. It's similar to what we had with recall, but now the denominator, instead of being the actual positives, is the actual negatives, right? So how many terms did I label as positive here, which in reality were negative cases. So divided by the sum of these two. This is known as the false positive rate. One way to think about it is, what proportion of innocent people did I convict? Or what proportion of healthy patients did I send to further testing, etc.? Right? What proportion of normal credit card transactions did I flag as fraud and annoy the client by telling them that they had filed a fraudulent transaction with a credit card, when in fact they just, I don't know, bought their coffee at a different coffee shop than their usual place. So this is called the false positive rate. The true positive rate is another name for recall. Right, we've already seen it. It's the ratio of true positives over this row of the table, and so these are two. True positive rate is just recall, but these are two related metrics. Now, another curve that we can look at based on these quantities is called the ROC. ROC stands for Receiver Operating Characteristic. It's a strange name. It comes from the fact that these ideas were developed back in during World War II, looking at radar, at the performance of radar. And so receiver operating characteristic is a term from electrical engineering and radar data analysis. But today we call them ROC curve. The ROC curve is similar to the one we had looked at before, but where now instead we look at the relationship as we change thresholds between true positive rates and the false positive rate, or again between recall. So it's a recall versus false positives curve. And in general, what we want is to have again, to balance a trade-off between false positives and overall detecting really as many true positives as we want, right? So we would like to have low false positives while having many true positives, right? We don't want to make mistakes, but we want to actually catch all of the cases that are positive, which means that we sort of want to be up here. So again, in the spirit of the previous one, we have so we want to be up here, and similarly we can ask what happens as we change our thresholds. So in this case, the same exact reasoning we had before shows us that as we have low thresholds, we are up in this part of the curve, and high thresholds end up somewhere in here. But ideally, again, the shape of the curve that we would like to have is this one for a perfect predictor. So again, we can compute what is the area under the curve for our real model and compare it to the area under the curve of the perfect case, which would have an area of 1. And so one way to sort of compare how is our model doing, so this is an example of our ROC curve for our real model, is to compare it to a purely random model. So this is an example of a model that is strictly random. You can find it in our notebook. So in our notebook, let's go over here. so that you can see how this particular model was created. This is an ROC curve, and by the way, scikit-learn has an ROC curve function built into it, and we've already seen that it has scikit-learn has metrics for computing confusion matrix, has methods for computing confusion matrix, matrices, ROC curves. It will also give us precision recall curves, etc. These are all basically out of the box, ready for you. But this is an example of an actual random model. So look, and here what we're saying is, for every game, we produce a uniform probability between 0 and 1. So we're truly just producing answers at random. And this is what, in general, the ROC curve looks like for a random model. So basically, our world lives between this curve right here, which is what kind of completely random answers would give, and the idealized world of this L-shaped. And all of the real world curves that we're going to get are going to be some kind of L-ish shaped here, whose area is going to get closer and closer to 1 the better they get. The purely random model, the diagonal, has an area under the curve of about 0.5, right? The square has an area of 1, and this is half, it's the diagonal that bisects it, so its area is half. And which means that in general, we're basically moving between AUCs of 0.5 and 1. We'll never quite get to 1, but if your model has an AUC very close to 0.5, you don't have a model. You don't have a useful model, because the random, basically producing random nonsense gives you already an area under the curve of a half. So you need to be moving as close to 1 as possible, but really not very close to 0.5. So these are some of the techniques that we have for evaluating classifiers. There's a lot more quantities you can compute. From these metrics. There's a link in here and here's a screenshot of the page on Wikipedia that summarizes all of the various quantities that you can compute based on these fundamental metrics from models. One important note, comment to make is that some of these metrics are purely based on predictions. Things like confusion matrices, accuracy, precision, and recall, they're basically drawn from the entries in the confusion matrix. Those are strictly based on the predictions. Whereas for things like the precision recall curves and the area under the curves, we actually have to have access to the underlying model, because at that point we're playing with a threshold, not just with the values of the predictions, but we're playing with a threshold, which means that those depend on the entirety of the model.